Formula mass. We've talked about atomic mass, the mass of an atom. We talked about molar mass, the mass of 1 mole of atoms. The formula mass is the mass of a formula unit, or the mass of the formula. It's also sometimes called a molecular mass or a molecular weight. Molecular weight is an older term that we're trying to get rid of. Still pops up. Molecular mass, the mass of a molecule. So the sum of the masses of the atoms in a single molecule or formula unit is what gives us the formula mass or the molecular mass. So the general idea here, formula mass, the number of atoms of the first element times the atomic mass of that first element, plus the number of atoms of the second element times the atomic mass of the second element. And this is like, buying stuff at the grocery store. If you've got 5 rock stars, how much is it going to cost? Well, it's 5 times the price of 1. And then if you throw in 3 Pepsis, well, it's 3 times the cost of the Pepsi, right? So all we're doing is finding the number of each and then multiplying by how much they weigh. So let's do an example. Calculate the formula mass of calcium nitrate. What do we need first? We need the formula. Dang, right? They gave us the name. We're going to make you practice. Calcium nitrate, what kind of compound? Molecular, ionic, or acid? Ionic. We recognize that because the first element is calcium, which is a metal. So we need formulas for ions, and then we'll look at the charges to put them together. So calcium is Ca. What's the charge? 2 plus. Because it's in group 2. Nitrate is what? NO3 minus. Why? Because. Okay, so now we have to put these two together. And some of you are still a little confused about how exactly to do that. If you're not getting that, please come and talk to me. I don't think me spending class time on it is necessarily going to solve anybody's problems, but I can help you one-on-one much more effectively. So we look at this and we've got a +2 charge and a -1 charge. We're going to need 2 of these guys to balance the charge on the calcium. Because we need more than 1 of the polyatomic ion, that's a very strange parenthesis there, we're going to put parentheses around it and put the number on the outside. Shrink wrapped it at Costco, and you got 2 of them on the conveyor belt. Now we have the formula. We're going to look at the formula and see, well, how many calcium atoms are in the formula? 1. So we've got 1 times the mass of calcium. That comes off the periodic table. So 40.078 atomic mass units. I'm using the periodic table on the wall here. How many nitrogens? 2. Because we have 2 of these packages, and each package has 1 nitrogen. So 2 times the mass of the nitrogen. Did I get that right? How many oxygens? 6. 6 oxygens times the mass of oxygen. Then you get your calculator out and you punch some buttons. My calculator is showing me 164.0878. The unit would be atomic mass units. Did anybody else get that number? Okay. I recommend that you write this out. I know that you could do it without writing it out. Write it out anyway. And then do the calculation twice, because it's easy to make mistakes. And if you get 2 different numbers, go for best 2 out of 3. What should we do with significant figures here? Yes?
Oh, I have a question. If we
Okay.
get within really close to that number, you mean that we'd be counting?
Well, what did you come up with?
164.093.
Did you use exactly the same masses that I did? No. So that's the difference. And that's a excuse me, that's a good question. Should I use the masses off my yellow periodic table, the inside cover of the book periodic table, the one on the wall? Use whichever one you like. Personally, I have a lot of them memorized to 4 sig figs just because I do them so often. And so that's why I have to keep looking at this one because I don't remember all of those. And I'm going to start just rounding them a little bit because I'm tired of turning around. When you use a different periodic table, and there have been some updates, and so you might see the masses very slightly different from table to table, even if it isn't just a sig fig issue, it should not cause a problem in your calculations. So use whichever periodic table you have easily available, okay? The thing I do not want you to do, and some students do this, do not round masses to whole numbers. Sometimes it won't matter, but sometimes it'll matter a great deal. And so we don't want to round this to 40 and this to 14 and that to 16. In this instance, it probably wouldn't matter very much. But if you round things like chlorine, which is 35.45, that's almost exactly between 35 and 36. That's going to cause some problems, and so you don't want to do that. I would say that the least number of significant figures you should use is 4. Okay? What I would do with this is I would treat this like it was just adding. I'm taking this and I'm adding this twice and I'm adding this 6 times. And so I'm going to have the smallest number of decimal places, which is this guy with 3. And so I would just underline there. Usually what we'll be doing is we'll be using these sorts of masses in calculations. And so you don't necessarily want to round it off just yet. Any other questions? Yes, there's a stuffed lemming on the pole. He's not my lemming, he's someone else's lemming. Molar mass. I want to get a stuffed mole and stick him on the pole. I've been told that this lemming moves from classroom to classroom occasionally, but he's been there for like a year and a half now. He's just stuck up there with magnets, I think. It's kind of cute. Okay. One of the classrooms I taught in had a big bank of windows, and there were bushes and stuff, and there were literally squirrels. And there were trees, and sometimes the squirrel would sit in the tree and stare at me while I was lecturing. You know, the joke about people getting distracted, you know, like the dog squirrel, you know, and they're off. I would literally get distracted by squirrels. Okay, so there's our squirrel episode. Molar mass. The molar mass of a compound is the mass of 1 mole of a compound. The number is the same as the formula mass, it's just the unit's different. And that's because of how Avogadro's number and the mole were defined. The numbers are the same, just the units are different. So what's the molar mass of ammonia? Well, we need the formula for ammonia. What's the formula? Close. NH3. NH3 is ammonia. NH4 plus is ammonium. Yeah, really close. So how do we find the mass of 1 mole of ammonia? Same way we did the formula mass. We're going to take, I'm going to actually write out all the units on this one. We have 1 mole of nitrogen. The mass of nitrogen, I'm going to start rounding. Bless you. 14.01 grams of nitrogen per mole of nitrogen. Plus 3 moles of hydrogen times the molar mass of hydrogen, 1.008 grams of hydrogen or mole of hydrogen. No, it's not 14, it's 17. Dang it. Come on. I forget the decimal places. Zero, 3, 4. Now, the way that I've rounded this, I'm going to have two significant figures. That's grams, and that is equal to 1 mole of ammonia. And so sometimes you'll see molar masses written per mole, so 17.03 grams per mole. That looks like a conversion factor, doesn't it? Any questions? Calculating molar masses is something that chemists do a lot. We can use the molar mass with Avogadro's number to count molecules by weighing them. The general idea here is that you take the grams of A, you convert to moles of A, and that is using the molar mass, and then you convert to molecules of A, and that's where Avogadro's number comes in. So, find, I forgot to fix the typo on this. Does anybody see the typo?
A table?
In a table. Find the number of ibuprofen molecules in a table containing 200 milligrams of ibuprofen. What? Tablet. Yeah. Yeah, it would be start chewing pieces off the table. So, find the number of molecules in a tablet, a pill, containing 200 milligrams of ibuprofen. These are just dimensional analysis problems. You might be thinking, just? No, they should be just. So we have 200.0 milligrams. Milligrams of what? Well, we're given the formula C13H18O2. That's the only number in the problem, so we're probably going to start with that. And then what are they asking for? Number of molecules. Well, we don't know a relationship between milligrams and numbers of molecules. What's the unit that's going to come directly before molecules? Moles. Because we can go from moles to molecules using Avogadro's number. Can we go from milligrams to moles? We can go grams to moles, so we can stick grams in there. Grams to moles. Can we do milligrams to grams? Sure we can. Easy. The path is the hard part. Write down the path if you're not getting these answers correct all the time. 200 milligrams C13H18O2. I look at my path, 3 arrows, 3 fractions. The units in the path become the units in the numerator. Milligrams to grams to moles to molecules. I really want there to be an abbreviation for molecule, but there's not. We can't use MOL because MOL is the abbreviation for mole. That saves you one stinking letter. MLC. We'll have to work on that. The problem is, if it's just in this classroom, then we get used to using it and we go outside and everybody's like, what the heck are you talking about? Okay, so units work out. We need to put numbers in here. Relationship between molecules and moles. 6.022 times 10 to the 23rd. It's a really long number, so it's not going to fit in there with that really long unit. And that's 1 mole. Relationship between grams and milligrams. What does milli mean? means 10 to the negative third. I've got milli in the bottom. I don't want to put what it means next to it. I have to put it on the top. 10 to the minus 3. It's 1 times 10 to the minus 3 on top, 1 on the bottom. Moles and grams. What number is that? It's the molar mass. We have to calculate it. So I'm going to do it the way I would like you to write it down when you show your work. We don't have to put all those units into this one because it's kind of a standard calculation. So 13 times the mass of carbon plus 18 times the mass of hydrogen plus 2 times the mass of oxygen. I'm using a periodic table where all of the molar masses are rounded to 4 significant figures.
And that would go on top, correct? And then grams on bottom.
You're getting ahead. That's okay. 13 times 12.01 plus 18 times 1.008 plus 2 times 16. 206.274. And that's grams per mole, or grams is equal to 1 mole. So the early question was, where does the number go? It's got to stay with its unit. So 1 mole of this compound weighs 206.274 grams. I'm not going to round my molar mass yet, because I'm not done with the calculation, and we don't round until the end. Now I've got everything in place, and I just put the numbers in, go across, multiply by the top, divide by the bottom. It's a big number. That's an understatement. How many sig figs should the result have? 4. Our starting number had 4 sig figs. This is exact. This had 5. As we wrote it, Avogadro's number there had 4. So this is going to come out to be 5.839 times 10 to the 20 molecules. Bless you. That's a really big number. Is it okay? Is it appropriate that that's a really big number? Yeah, because we're counting molecules. Question?
So our starting number is not always going to dictate our sig fig.
The starting number will not always dictate sig figs, but oftentimes it does. And in this case, it does. We could add the 1,4 on Avogadro's number if we needed to, but usually in the problems that we'll run into, we're going to have 3 or 4 significant figures in the mass or whatever that's given, and that ends up limiting our answer.
When we're multiplying this, we do include the first number.
When you're multiplying, yes, you include the first number. So you start with this, and I think it's best to follow a pattern and multiply by the top, divide by the bottom. Multiply by the top, divide by the bottom. Multiply by the top, divide by the bottom, press equals. And that way you won't overlook something. Any other questions?